following Sequoia video explores some workflows using the Fort Mason dataset. First, we'll explore the content of a point file. We have a folder containing 49 sources scanned from different points around the buildings. And since we don't have a cache yet, we'll let Sequoia just preview the content of the original PTG source file. We can see where the scanner was placed, and this is just one fragment. We can orbit around and take a look, and let's adjust the point size and the point opacity a little bit so we can see better what data we have here. Now we could build a cache for this source file. Right now the cache is missing, but if we hit the button it would create a cache. Let's not do that because we have 49 different cache files, and doing this manually wouldn't be a good idea. So let's batch convert all the 49 files in the folder. If we select this option, a dialog opens and we have 49 entries where the output path is the same as the input path, and the output file name is going to be right now the same as the input. We'll select all the files and we'll repath them to write to a convert directory. And we can also modify the output file, for example adding a suffix in this case. And of course the data type is different, so even if we were writing into the same folder it wouldn't be a problem. We can enable the single output file option if we wanted to combine all 49 into a single output file, but right now we'll convert each one individually. And the reason we'll do this is we can use the multitask capabilities of Sequoia. It runs multiple tasks in multiple threads, and each one of those tasks can use more than one thread. If we take a look at the configuration settings on the tasks, the CPU normal priority task is currently set to 6, and if we set it down to 1, the tasks that are currently running will finish and no new task will be scheduled until only one single task is running. Right now all of them are saving to disk, and if we take a look, the CPU load is not very high. The saving uses a little bit more CPU, but otherwise it can fall really low. We can increase the number of allowed parallel tasks, for example to 8. We have currently 8 threads, and we can potentially even request 16, even though we have only 4 CPUs with hyperthreading, so 8 threads altogether. But you'll notice that even now we're not getting 100% CPU usage all the time, and this is because the data is being read and written through a NAS drive, and the network I/O is in this case the limiting factor. If we're using the local drive or an SSD drive, for example, it would be much faster, and all the CPUs would be loaded at 100%. Let's set it back to 8 and let it finish. Next we will load the multiple converted files. We use the batch import multiple files option. We'll select all 49 and we'll create objects that are named exactly like the files that we are reading. We can select a few of them, let's say 2, and we'll force them to auto load. So out of 49 objects that were created, only 2 will actually load the points immediately in the viewport. Next we'll combine the files and export a subset to disk for meshing. So let's create a point region of interest bounding box around our dataset and adjust the bounding box so we can save only the points we're interested in. In the next step we'll hit the export in world space button and we'll define our name, Fort Mason main building only. The saving will start. It will go through all 49 files, but let's not wait for that. So let's take a look after the combining of the files. We'll try to mesh them together. We'll create a single loader with all the combined data. We have about 352 million points on disk, but we are displaying only a fraction in the viewport for speed. And we can create a mesh object, a mesher. It picks the point load automatically, and then it scans it to figure out the optimal radius for meshing. So we can set our radius to the suggested value, and we'll use the HACKSAW feature. Since our building is very long along the x-axis, we'll use 10 iterations, 10 subdivisions along that, and 4 along the other 2 axes. We'll create an output folder and define output name. If we take a look at the task manager, now we have 160 tasks for meshing. Eventually they will start running in parallel, but instead we'll try to use multiple machines on our network to do the same work in the background while we are using Sequoia for other things. So we'll press the export on deadline button. In this case, we'll have to define exactly the same output path somewhere on the network where all the machines can write through. Our file is on the NAS, so all the machines will see it. We can set the pool and the group and submit to deadline. Sequoia now communicates with deadline and starts watching for the progress of the job it submitted. We see that a bunch of machines have already started processing. And if we take a look in Sequoia, the progress bar that is displayed there corresponds to the progress bar that is displayed in the deadline monitor. After all the tasks of the job have been processed, we can see that all the machines worked on the job, and some were faster than others. For example, there was a Surface Pro tablet that was also participating in the meshing, but was taking about 7 minutes instead of 30 seconds. In the next step, we'll load the resulting meshes. We can go to the Batch Import Multiple Mesh Files menu and select all 160 entries. We could load them all, but let's cancel this because we don't want 160 objects if we can use a single one. We'll create a single mesh loader. We'll tell it to load all the multiple partitions, all 160 of them, and we can switch to a view that looks at the whole building. Let's change the home grid to 10 meters spacing, and we'll change the segments to 20 for each quadrant. Now we could update our mesh loader and it will start reading the mesh partitions from disk, and will slowly build the whole structure. In the beginning it's loading the vertex cloud, and later it will load also the faces, and we can disable the interactive lighting because the vertices also have a vertex color from the scan, so we don't really need that. After a while the whole mesh will be loaded. We can refresh the thumbnail of the bookmark to show the loaded geometry. We can navigate around it and see the whole building. Now let's project an image on the geometry. During the Rio 2015 conference in San Francisco, I took a picture with a cell phone of this same building. So let's create an image projection object and pick that image, and it will be projected, for now incorrectly, on the geometry. So we'll have to align it. Currently it's set to projection mode perspective, which is correct. And what we need to do is open the image in an image viewer. We'll dock the image viewer as a second tab in the same panel as the viewport, so we can switch between the two. And we'll create some markers in the image and in the viewport. We can hide for now the projection. We'll disable projection on geometry in the viewport temporarily while creating the markers. When we create a marker and double click it, it automatically switches the corresponding image view and the marker gets selected. So all we have to do is right click and say place selected marker here. Then we can create another marker which also has a scene corresponding marker, and we can right click and say place selected marker here, and now we have the two corners of the building. Then we can grab this one and we can move it with the mouse if we want and put it in the corner of the entrance, and create a fourth which will be in the bottom right corner of the building. So once we have the image markers, we can go to the scene by double clicking the scene markers, and so we can switch to move mode. We can move with the gizmo, but it's much easier to right click and say place selected object here, and then repeat for each marker. Double click, right, and select the object here, and then the next one, and then the last one in the bottom right corner. And once we have all the markers set, we can enable the projection in the viewport, and we'll hit the button, calculate alignment, and we get our projection.